Hello students, in this video we're going to see learn more about points of inflection. Now there are two types of points of inflection, in fact, stationary and non-stationary. But before that, let's say, now I hope you know that concave down and concave up. So now if I say if it looks like this, so this part is basically concave down, concave down. Now let's say if the curve is like this, now this part is concave up. Yeah, concave down and concave up. Okay, now what is a point of inflection? To put it simply, a point of inflection is a point where the concavity changes. Now for example, if you have like this, let's say like this, okay, now here, let's say this here, a point here, the concavity changes, isn't it? So here it was concave down and here it is concave up. So at this point it ceases to be concave down and it starts becoming concave up. So let me repeat it again. A point of inflection is the point where the concavity changes, where the curve changes from concave down to concave up, or it can be the other way around, vice versa. It can be concave down to concave up, or concave up to concave down. So that is a point of inflection. Now as I mentioned, there are two types of points of inflection, a stationary point of inflection and a non-stationary point of inflection. Okay, in fact we are going to learn more about both these kind of points of inflection with diagrams. So let us continue. Yeah, now there is one more thing that that you should know. Now if you observe the behavior of the function before and after the point of inflection, it will be same. I mean, behavior in the sense, for example, here the function is increasing before the point, and even after the point of inflection the function is increasing. Okay, so same way you have something like this. Let's see, you have something like this here. If let's say if this is the point of inflection, now before the point of inflection the function is decreasing, and even after the point of inflection the function is decreasing. Okay, so the function increases even before and after the point of inflection, or decreases before and after the point of inflection. So what it means is f dash of x. Now in this case f dash of x will be positive, and here also f dash of x is positive, right? That means before and after the point of inflection the first derivative will have the same sign. Now in this case also, let's say here f dash of x is negative, this is the point of inflection, and here also f dash of x is negative. Okay, so in fact this is a very important point. Before and after a point of inflection the first derivative will have the same sign. It is true always. Okay, so point number one is that. Okay, now let us look at this graph of the function y equal to x cube. You see here this part is concave down and this part is concave up, right? Concave down and this is concave up. Okay, now here at this point the concavity changes. Okay, so let me find out. So what you do is I'll write f of x equal to x cubed. So as I told you, at the point of inflection and before and after the point of inflection the first derivative has the same sign. So let me check whether it is true or not. So f dash of x equal to 3x squared. Okay, now let me equate 3x squared to 0. I'll get x as 0. So let me draw the number line and let me draw 0. Now let me take a point more than 0. let's say 0.1 and substitute the first derivative. So f dash of 0.1 is 3 into 0.1 the whole square, which is positive. So here, if you take any value of x, f dash of x will always be positive. Now f dash of, let me take a value here, let's say less than 0, let's say minus 0.1. It will be 3 times minus 0.1 the whole square. Again it will be positive. So here also f dash of x is positive, right? So as you can see, before and after 0, f dash of x has the same sign, right? So, and this is stationary point as well. So now, is it a point of inflection? Is this sufficient to say that this is a point of inflection, that the sign of the first derivative remains the same, or the function before and after the point of inflection increases and increases, before the point increases and after the point is also increasing, or it is decreasing before the point and decreasing after the point as well. Okay. Now, for a stationary point, these two conditions are sufficient, student. That means the condition number 1 is the first derivative is 0 at that point, and the condition number 2 is the first derivative before and after that point has the same sign. That means positive before and positive after, or negative before and negative after. If these two conditions are satisfied, definitely that particular point is a point of inflection, a stationary point of inflection. So here in this case, the 0 is a stationary point of inflection. Okay, let me find this is you're seeing the graph of the original function. So let me try to draw the graph of the derivative function. Okay, now we know that if f of x equal to x cubed, then f dash of x is nothing but 3x squared. So this is a quadratic function. In fact, it will give us a parabola, isn't it? Let's just open at the top. So the parabola will look like this, right? So this is the graph of f dash of x. Okay, now you can notice something here, students. This is a point of inflection, right? This is a point of inflection. Now what is f double dash of 0? What is f double dash of 0? Is it positive or negative or 0? Now f double dash of 0, or let's put it this way, f double dash of x is nothing but, this is slope of tangent to the curve of f dash of x. So f double dash of x is the slope of tangent to the curve f dash of x. So how is it? For example, we know that f dash of x is the slope of tangent of the curve f of x, isn't it? Same way, f double dash of x is the slope of tangent to the curve f dash of x. Now this is f dash of x, the graph of f dash of x. So when I try to find f double dash of 0, it means I need to find the slope of the tangent at this point. Now definitely if I draw a tangent here, it will be parallel to x-axis. So f double dash of 0 will also be 0. Okay. Now we notice that at 0, the first derivative is 0. In fact, and the second derivative is also 0. So you might wonder whether it is true for all stationary point of inflection, whether for all this stationary point of inflection, whether the second derivative will be 0. Let us see another example. Okay, now let us consider this function, students, f of x equal to x minus 2 the whole cube. Now as you can see, this is 2. Now here it is concave down and here it is concave up. So definitely 2 is actually a point of inflection because the concavity changes there at 2. Now how do we know that it changes at 2? How do you know that it is not some other point? Very simple. So let me first find the first derivative, f dash of x. So f dash of x is 3 times x minus 2 the whole square, isn't it, into 1. using the chain rule. Okay, now I need to find the stationary points. Let me find it. So 3 times x minus 2 the whole square equal to 0, which will give me x equal to 2. Okay, so 2 is a stationary point here. Now we all know that for a stationary point to be a point of inflection, the first derivative should have the same sign before and after 2. If that is satisfied, then definitely it is a stationary point of inflection. Okay, let me take a value more than 2. Let me take let's say 2.1 and substitute in the f dash of x. So f dash of 2.1 is 3 times 2.1 minus 2 the whole square, so which is definitely positive. Let me take a value less than 2, let's say 1.9. So f dash of 1.9 equal to 3 times 1.9 minus 2 the whole square. Again it will be positive. So before and after 2, f dash of x is positive. So what does it mean? It means x equal to 2 is a stationary point of inflection, right? Stationary point of inflection. Okay, now you have to notice one more thing, students. At 2 the concavity changes, the graph becomes concave down to concave up. Before and after 2 the function is increasing, which means before and after 2 the first derivative has the same sign. So it is a stationary point of inflection. Okay, so we know that f dash of 2 is 0, isn't it? F dash of 2 is 0 because it is a stationary point. Now what if we want to find f double dash of 2? If you recall, in the previous problem, f of x equal to x cube, we found out that at the point of inflection, the second derivative was also equal to 0. So let me check whether it is true here as well. Okay, so let me erase this. Okay, so if I try to draw the graph of the derivative function, so this is f dash of x, this is x. So 3 into x minus 2 the whole square. So let's say this is 2. So this is how the graph will look like, right, students? It will be a parabola. Now if we want to find f double dash of 2, then which means slope of the tangent. Okay, this is the curve. Now at 2 I will draw a tangent. Let's say this is a tangent, and that slope, the slope is f double dash of 2. Now we know that here the slope is 0, so f double dash of 2 is equal to 0. So in fact it will always be true, students. So whenever you have a stationary point of inflection, the second derivative will always be 0. Okay, provided the second derivative exists. Okay, so let me go through it once more. Let me put it in writing. Okay, so x equal to a gives a stationary point of inflection if f dash of a equal to 0, the first derivative is 0, and point number 2, f dash of x has the same sign before and after a. And we also found out that f double dash of a will always be 0. Okay, this is another important point that you need to keep note of it. Second derivative at the stationary point of inflection will always be equal to 0. So let us see an example where we can find a stationary point of inflection without drawing a graph. Okay, now let us consider this function f of x equal to 4x cubed minus x power 4. Now this particular function has a stationary point of inflection. So let us see what it is. So first find the first derivative. So f dash of x equal to 0. F dash of x, I have to find the first derivative. So f dash of x equal to 12x squared minus 4x cubed. Okay, now to find the stationary points, I will equate this to 0. So 12x cubed minus 4x, 12x squared minus 4x cube equal to 0. So let me factorize it. Let me take 4x squared common. So I'll get 3 minus x equal to 0, which means either x equal to 0 or x equal to 3. So let me draw the number line now. I'll draw a number line. So I'll put 0 here, I'll put 3 here. Let me take a value more than 3 and substitute in f dash of x. So let me take, for convenience sake, let me take 4. So f dash of 4 is 12 times 4 square minus 4 times 4 cube. So which is nothing but, so we'll get minus 64, so negative. So f dash of x is less than 0 after 3. So now let me take a value between 0 and 3. Let me take, let's say, 1 and substitute in the first derivative. F dash of 1 is 12 times 1 square minus 4 times 1 cube, so which is 8, so positive. So f dash of x is positive. Let me take a value less than 0. Let me take, let's say, minus 1. So f dash of minus 1 is 12 times minus 1 the whole square minus 4 times minus 1 the whole cube. So answer is 12 plus 4, which is 16, again positive. So f dash of x is positive, right? So as you can see here, before and after 0, f dash of x has the same sign. So therefore this is a stationary point of inflection. This is a stationary, this gives us a stationary point of inflection, right? Okay, now this 3 that you see here, it will give us a local maximum value, because before 3 first derivative is positive. That means the function is increasing, the function is increasing, f of x is increasing, and after 3 f dash of x is negative. That means f of x is decreasing, right? That means this 3 will give us local maxima. Okay, so this particular function has two stationary points, 0 and 3. One of them gives us a stationary point of inflection and the other one gives us a local maxima. Okay, now we also notice that at the point of inflection the second derivative will always be 0. So let me cross check in this particular problem. Okay, so f double dash of x will be 24x minus 12x squared. Okay, so let me substitute the 0, which is a stationary point of inflection, in the second derivative. So f double dash of 0 is 24 into 0 minus 12 times 0 squared, so which is nothing but 0. So as you can see, the second derivative is also 0, right? Now, what do you mean by non-stationary point of inflection, students? As the name suggests, it is not a stationary point, but still it is a point of inflection. What it means is, at that particular point, the concavity changes from concave down to concave up, or concave up to concave down. Okay, so that is a non-stationary point of inflection. So let us see. Let me draw a diagram to explain it further. Okay, now look at this diagram, students. Look at this diagram. Now at P, now here it is concave up and here it is concave down, but this is not a stationary point. Yeah, so the reason is f dash of x1. So f dash of x1 will not be equal to 0, isn't it? Because if I draw a tangent at that point, it will not be parallel to x-axis. So this is a non-stationary point. But meanwhile, the concavity changes, right? At this point, before the point, the curve is concave up. After the point, before the point, it is concave up. After the point, it is concave down. So this is a non-stationary point of inflection. Okay, and also one more thing. before and after the point, you can see here in this part f dash of x is positive, and here also f dash of x is positive. So what it means is, like the stationary point of inflection, even for non-stationary point of inflection, the first derivative, the sign does not change before and after the point. Okay. Now we also notice that at a stationary point of inflection, the second derivative will be 0. So is it true for a non-stationary point also? Definitely. Now look at this diagram. Now here the green colored curve gives you the graph of f dash of x. Now you can see at x1, so if you want to find, let's say, f double dash of x1, which is nothing but slope of the tangent. That means I draw a tangent here, and the slope is f double dash of x, right? So here, since the tangent is parallel to x-axis, so the slope will be 0. So f double dash of x1 will be 0. So even for a non-stationary point of inflection, the second derivative will always be 0, right? So let me rephrase it. Okay, so x equal to a is a non-stationary point of inflection if these three conditions are satisfied. The first one is the first derivative, that is f dash of a is not equal to 0. That means the first derivative will not be 0 at x equal to a. And the second one is f dash of x has the same sign before and after a. So if we draw a number line, you will notice that before and after the non-stationary point of inflection, the first derivative has the same sign. And the third condition is the second derivative has to be 0. Okay, at a non-stationary point of inflection, second derivative has to be 0. If these three conditions are satisfied, then definitely that x equal to a is a non-stationary point of inflection. That means it is a non-stationary point, but it is a point of inflection because the concavity changes at that point. Okay, so let me see an example. I'm going to show you how to find a non-stationary point of inflection. Okay, let us consider this problem. So let me find f dash of x. So f dash of x is 3x squared minus 6x minus 9. So let me find the stationary point. So 3x squared minus 6x minus 9 equal to 0. So this will give me x squared minus 2x minus 3 equal to 0. So if I solve it, I'll get x equal to 3 or minus 1. Okay. Now there are two stationary points. Let me find the nature of these stationary points, whether they will give me a point of inflection or a maxima, local maxima or a local minima. So how do we do that? I can find, either use the first derivative test, or I can use the second derivative test. Let me use the second derivative test. So f double dash of x is 6x minus 6. Okay, so let me put 3 first in second derivative. F dash double dash of 3 is 6 into 3 minus 6, which is 12, so positive. So which means x equal to 3 gives local minima, right? Okay, let me substitute minus 1 in the second derivative. So f double dash of minus 1 is 6 into minus 1 minus 6, which is minus 12, less than 0. This means x equal to minus 1 gives local maxima. Okay, so these two stationary points, one gives us local maxima, another one gives us local minima. Now so definitely there is no stationary point of inflection, but does this function, does it have a non-stationary point of inflection? For that, what you need to do is, I hope you recall, there are three conditions for a non-stationary point of inflection. The first derivative should not be equal to 0, and the sign of the first derivative remains the same before and after that point. And the second derivative, third condition is second derivative has to be 0. Okay, so the second derivative is 6x minus 6. So let me equate that to 0. So 6x minus 6 equal to 0. So which means x equal to 1. Okay, so the first condition is satisfied, that is f dash of 1 is not equal to 0, isn't it? Yeah, because only 3 and minus 1 are the stationary points. And the third condition, this is the first condition, then the third condition is f double dash of 1 should be equal to 0. That is also true. Okay, first and third condition are satisfied. So what is the second condition? The before and after 1, the first derivative should have the same sign. Let me check. So 1 here. So let me take a value more than 1 and substitute in the first derivative. So let me take let's say 1.1. So f dash of 1.1 is 3 times 1.1 squared minus 6 times 1.1 minus 9. So which will give me, so this will give me minus 11.97, which is negative. So f dash of x is negative. So let me take a value less than 1. For convenience sake, let me take 0. So f dash of 0 is 0 minus 9. So again, f dash of x is negative. So the second condition is also satisfied, right? The before and after 1, the first derivative has the same sign. So what it means is, here x equal to 1 is a non-stationary point of inflection. In fact, if you draw the graph, you will notice that at 1 the concavity changes. Yeah, you can check it in your GDC. So let us see one more problem. Okay, so what you see here is the graph of e raised to minus x squared. Now as you can see, this graph has a local maximum, which is this, and it has two points of inflection. That means where the concavity changes. It is quite easy to find. So one point is here. Okay, here it is concave up and here it is concave down. So the concavity changes, but it is not a stationary point, and the other point is here. Okay, here it is concave down and here it is concave up. Okay, now so let me name it as, let's say A and B. Now how can you find the coordinates of A and B? Yeah, we know that it is a, I mean it looks like a point of inflection. Suppose they are point of inflection, how can I find out the coordinates? Very simple. You need to find the first derivative first. So f dash of x is e raised to minus x squared into minus 2x. Yeah, and as you can see, A and B, both of them are non-stationary point of inflection. So definitely f dash of x will not be 0. So, but f double dash of x will be 0. So let me find f double dash of x. F double dash of x. So I need to use the product rule. First, let me differentiate this. That is e power minus x squared into minus 2x into, I'll keep the second function as it is, minus 2x, plus. Now I'll keep the first function, that is e power minus x squared, as it is, and I'll differentiate the second function, which is minus 2. So this will give me 4x squared into e power minus x squared minus 2 times e power minus x squared. So if you take e power minus x squared common, you will get 4x squared minus 2. Okay, now to find the coordinates of A and B, you need to equate the second derivative to 0. So I will do it here. So e power minus x squared into 4x squared minus 2 equal to 0. Now e power minus x squared can never be 0, because e power anything, the exponential function can never take 0 as one of its values. So definitely it means 4x squared minus 2 is 0. So x squared is 1 by 2. So x is plus or minus 1 upon root 2. So this point will be minus 1 by root 2 comma some y value, and this point will be 1 by root 2 comma some y value. Okay, you can find that value by substituting in the original function. Okay, now you can also observe that before and after this point, the first derivative has the same sign. You can see very clearly the function is increasing, so f dash of x is positive, and here also the function is increasing, so f dash of x is positive. Right? Same way here, before b f dash of x is negative, and after b also f dash of x is negative. So these two, a and b, are non-stationary points of inflection. Yeah. So let me let us recollect it. So to find a non-stationary point of inflection, the first step is find the first derivative, and the next step is find the second derivative, equate the second derivative to 0, and check whether you get any value, and then take that value, draw the number line, and check whether the first derivative has the same sign before and after that point. If it satisfies, if all these conditions are satisfied, then definitely you get a non-stationary point of inflection, right? Okay. Let us do one more problem, students. X power 4 minus 4x cubed. So let me find f dash of x first. F dash of x is 4x cubed minus 12x squared. Okay, so let me find the stationary point. So 4x cubed minus 12x squared equal to 0. So I can take 4x squared common. I'll get x minus 3 equal to 0. So which means either x equal to 0 or x equal to 3. Okay, so let me find the whether 0 and 3. Let me find the nature of the stationary point 0 and 3. So let me find f double dash of x. F double dash of x equals 12x squared minus 24x. Okay, so let me substitute the stationary points. F double dash of 3 is 12 times 3 squared minus 24 times 3, which is positive. So x equal to 3 gives local minimum. So let me substitute f0 in the second derivative. So we'll get 0 minus 0. So okay, so f double dash of 0 is 0. So I don't know, it might be a point of inflection or it might be a point of maximum and minimum. So how do I find out? The only way to find out is to draw the number line, write 0. Now take a value more than 0. Let's say, let me take 1 and put in the first derivative. So f dash of 1 is 4 minus 12, which is negative. So f dash of x is negative after 0. So let me take a value before 0. So let me take minus 1 and substitute the first derivative. F dash of minus 1 is 4 times minus 1 the whole cube minus 12 times minus 1 the whole square. So again you get a negative answer. So f dash of x is less than 0. So that means the first derivative has the same sign. So this 0 is a stationary point of inflection. Okay, so as you can see, this particular function has a stationary point of inflection and also has a point of local minima. Okay, now does this function has a non-stationary point of inflection also? So let me check it. Let me erase this. Okay, so to find a non-stationary point of inflection, as you recall, f double dash of x has to be equated to 0. So 12x squared minus 24x equal to 0. So let me take 12x common. 12x into x minus 2 equal to 0. That means either x equal to 0 or x equal to 2. Now we already know that x equal to 0 is a stationary point of inflection. So let me check x equal to 2. So let me draw the number line 2. So let me take a value more than 2. So let me take 2.1 and substitute in f dash of x. So f dash of 2.1 is 4 times 2.1 the whole cube minus 12 times 2.1 the whole square. So this will give me minus 15.9, which is negative. So f dash of x is negative after 2. Let me take a value before 2. So let me take maybe 1. F dash of 1 will be 4 minus 12, which is negative. So again f dash of x is negative. So it means that this 2 is a non-stationary point of inflection. Yeah, because the first condition is satisfied, that is f dash of 2 is not equal to 0, and that is the first condition. And the second condition is satisfied here, that is before and after 2 the first derivative has the same sign, and the third condition is satisfied here, that is f double dash of 2 equal to 0, right? So this function has a stationary point of inflection and also a non-stationary point of inflection. Okay, and one more thing, one important thing that you need to know is that let's say if A is a point of inflection, let us not worry about whether it is a stationary point of inflection or a non-stationary point of inflection, but if it is a point of inflection, then f dash of x will have the same sign. So here f dash of x is positive, means here also f dash of x will be positive, right? So before and after the point, the first derivative has the same sign, but in case of second derivative, what will happen is the sign changes. So here f double dash will be 0, f double dash of a will be 0, and before and after a, for example here you can have f double dash of x will be, let's say, negative, and here f double dash of x will be positive. So before and after a, the second derivative will have different sign always, but the first derivative will have the same sign and the second derivative will have different signs. So let me explain it with the diagram. Okay, so before proceeding further, let me recollect the concepts of slope of a straight line, which you must have learned in earlier classes. So let us say you have a straight line here. Okay, we all know that this has a positive slope. So let's say if this angle is theta, then the slope is tan theta, isn't it? Tan theta. And since here theta is acute, tan theta is positive, so slope will be positive. Okay, so now let me draw another line. Let me draw a line here. So this is let's say this is line 1 and this is line 2. So let me take, let's say this is say 45 degrees, and let me take this as 60 degrees, even though it looks more than that. Okay, now which line will have a bigger slope, students? So definitely the line L2, because for this one the slope is tan 45, which is 1, and for this one the slope is tan 60, which is root 3, isn't it? So root 3 is more than 1, so slope of L2 is more than slope of L1. In fact, what happens is suppose if I draw a line like this, and then line like this, and then line. So what happens is the slopes are increasing. In fact, let me draw this. This will have a negative slope. So the slopes are increasing. So if you go anti-clockwise, so L1, L2, L3, L4. So L2 will have a bigger slope than L1. L3 will have a bigger slope, greater slope than L2 and L1, and L4 will have the highest slope among all these four lines. And when you go clockwise, that means this way, then the slopes will decrease. Okay, clockwise and anti-clockwise. Okay, so we're going to use this concept now to make you understand the concept of points of inflection. Okay, in this diagram, this is y equal to f of x. I have drawn part of the curve y equal to f of x. Now we know that here f of x is increasing, isn't it? F of x is increasing. Therefore, f dash of x is positive. Okay, but what about f dash of x? Like here, when you take points here, what happens to f dash of x? Is it increasing or decreasing? Okay, so let me draw a tangent here. So if you draw a line, the slope will be f dash of x. So here, this is the slope. The slope of this line will be f dash of x. If you take here, so like this. As you can see, the slopes are decreasing, isn't it? Which means that f dash of x is decreasing, right? Which means that at these points, on the curve, f double dash of x will be negative. If f of x is increasing, then f dash of x is positive. If f of x is decreasing, then f dash of x is negative. Same way, if f dash of x is decreasing, then f double dash of x will be negative. So this is concave down, isn't it? This is concave down. So if we take the points which lie on the part of like where you have concave down, then second derivative will always be negative. Okay, and vice versa. That means if we take the points on the curve where it is concave up, then the second derivative will be positive. Okay, so if we take a concave down, so at all these points, f double dash of x will be negative. So if we take concave up, then at all these points, whatever point you take, at all these points, f double dash of x will be positive. So this is something you need to remember.